Yeah, first of all, thank you to the organizers for organizing this nice workshop with beautiful team, I think. So I'm very enthusiastic about chaining methods and in particular about their applications in compressed sensing and also in what I'm going to talk about today, random dimensionality reduction. So this talk is motivated by doing computation on a data set which consists of very high dimensional vectors. So we have a set of vectors placed in Rn that we would like to do some computation on. And since this is expensive or maybe not even feasible because we have storage issues, we want to embed this set into a lower dimensional space. And preferably, we would like to reduce the dimension as much as possible. Okay, so that's what's written here. And well, these benefits should be obvious to this audience, I would say. Okay? So the idea behind this, or the philosophy, is that although we often encounter sets of vectors that lie in a very high dimensional space, this set of vectors is actually not completely high dimensional in the sense that it has low intrinsic dimensionality. It has some sort of structure which makes sure that we can actually compress this set and still retain information on the set so that we can still do computations on it in a lower dimensional space and in that way speed up computation. However, what we understand under the intrinsic dimension of the set will depend on, well, basically two things. First of all, the kind of structure that we want to impose on this dimensionality reducing map. And also on what kind of structural information we actually want to preserve on the vectors. Okay? So today I will look at a scenario where we want to have three properties. So we want to look at a map that is linear. So it's represented by some matrix, which I will always call phi in this talk. And also we want to construct this this embedding in a way that is oblivious to the data. So I don't want to look at my data, but simply construct it independently of it. And what we will actually do is construct a random matrix to do the job, eventually. Okay, and then we have to fix what kind of information we want to preserve. And like I said, the amount of dimensionality reduction that we can actually achieve here really depends on what kind of information we want to preserve. And in this talk, I will fix it as follows. We want to get an epsilon isometry on the data set. So this means that we preserve interpoint distances of the data vectors in my set up to some multiplicative error epsilon. Okay? And you can think of this as somehow saying that I want to preserve the Euclidean structure of my data set. Okay? And this is relevant for many, many applications. And the way I will phrase this result is in a little bit of different manner. So X will be my original data set. And I will form a set T, which consists of all the normalized differences between these vectors. And then requiring this, so this epsilon isometry property, is the same as requiring that this constant, epsilon T, is smaller than epsilon. Okay, and it's a very, very short computation to show that this epsilon T is actually the smallest epsilon that you can pick in these inequalities. Okay? So to connect this a little bit with the previous talk. So in the previous talk, we looked at the scenario where this set X was actually the set of S-sparse vectors that we wanted to preserve. And this matrix phi was a subsample discrete Fourier transform. Okay? So this is sort of the compressed sensing scenario. And we've seen that if we have this kind of a property with epsilon small enough that we can reconstruct all S-sparse vectors using some efficient procedure. Okay, but in this random dimensionality reduction, although this looks a bit similar, we have a bit different aims. So first of all, we could be interested in a very different set of vectors here, so a very different initial data structure. For example, we might have data that lies on a low-dimensional subspace or on a manifold that we would like to preserve. Okay, so what we would like to do in the end is analyze how far I can reduce the dimensionality of the data while keeping this epsilon t small, okay? And we want to investigate how this embedding dimension, so the amount of dimensionality reduction that I can actually achieve, depends on the structure of this data set. Another difference with compressed sensing is that, as was explained in the previous talk, is that in compressed sensing, this matrix actually describes a real-life sensing system. So this means that there are some physical constraints that are imposed on you that will give you a structured matrix. And you can turn it into a random matrix by doing things like random subsampling, but you don't have full control over it. Here, in this dimensionality reduction problem, we can do anything, right? We can simply construct this random matrix as we please. Okay, and we will do this so that we get an efficient computational map and to also get very good dimensionality reduction results. So now I can pose the same question as in the previous talk and ask you, what is your favorite random matrix that you would like to use for this purpose? So I think we have a mix of people here. There are some excellent probabilists here. And I think they would say I would pick a Gaussian matrix, because this has beautiful properties. We know everything about Gaussians, and I can do very good analysis with that. So that's the scenario I will consider first. And then later, I will move towards an answer that will be appealing to computer scientists. Okay? So we will see that these Gaussian matrices are actually not so attractive from a certain perspective. Okay, I mentioned some possible applications here. So you can use these kind of transforms with this property to speed up some procedures like approximate nearest neighbors, approximate k-means clustering, constraint least squares program, also a manifold learning. So I won't talk too much about these applications here, okay? So I will focus on this fundamental dimensionality reduction question. The only thing I will show briefly is what kind of results you can get for constraint least squares at some point. All right, so let's first look at the scenario where I do my dimensionality reduction with this nice Gaussian matrix. And this is completely understood, and the central quantity that plays a role here is the first thing that appeared in Jelani's talk this morning, which is the Gaussian mean width of this given set T in Rn. Okay, so it's the expected sup of this inner product with a standard Gaussian vector. And a complete understanding of this dimensionality reduction question that I posed was already answered a long time ago by Gordon in '88. So I'm going to look at these sets of normalized differences all the time, so we can now think of T as being some arbitrary set on the unit sphere. Okay, and what Gordon's theorem says is that if phi is an m by n standard Gaussian matrix, and m scales like this, so it scales like epsilon to the minus 2 times the squared Gaussian width plus the log of the inverse failure probability, then this rescaled Gaussian matrix will be an epsilon isometry on T, okay, with probability 1 minus eta. Okay, so let me explain this, this result a bit more and connect it to some familiar things. So first of all, what we can say is that this is some sort of instance optimal version of the JL lemma. So a result that you've probably seen as a computer scientist at some point is this result where this squared Gaussian width is replaced by the log of the number of points that you have in your data set. Okay, so this is the Johnson-Lindenstrauss lemma. And the remark that I make here, and this is something we've already seen this morning in Jelani's talk, is that this squared Gaussian width is always smaller than the log of the number of points, but it can be much smaller if the set has additional structural properties. For example, if we return to the scenario of the last talk, if T is the set of k-sparse vectors, then the squared Gaussian width is bounded by k log n over k. Okay, and actually what you see in many, many applications is that, that this result, so this dimensionality reduction with a standard Gaussian matrix is actually optimal. Okay, so for example, for low-rank matrices, these k-sparse vectors, you can get this set for an arbitrary this result for an arbitrary set of finite vectors back, which is also optimal in a certain sense, in a worst case sense. So this is a very, very good result. Okay, another thing I'm going to talk about first is an extension of this theorem to random sign matrices, or a bit more generally, sub-Gaussian matrices. So Gordon actually didn't use any chaining at all when he proved this result. He actually used properties of Gaussian random variables very smartly. And actually, for people who know this, this follows from generalization of Slepian's lemma, which is known as Gordon's theorem as well. Okay, so that's one way to prove it. However, later people got interested in extending this to sub-Gaussian matrices, and in particular, I'm not really going to talk about this, these sub-Gaussian matrices much, so you can simply think of a random matrix which is filled with random coin flips, okay, IID. Okay, and then what Klaartak and Mendelssohn essentially already showed in 2005 is that this type of Gordon theorem holds. The only thing that they didn't get right is the dependence on this failure probability. This was later fixed, and afterwards a lot of people gave different and simplified proofs of this result. So now, what I would actually like to do is show you one proof of it, the most recent one. And I picked this one because it's closest to Jelani's talk, actually. So closest to your background, let's say. But first, before I do that, I want to talk a little bit about this Gaussian width parameter. Because what we will see is that actually all these proofs are based on chaining, based on Bernstein's inequality. And the result that you actually get is the same bound, but not with the squared Gaussian width, but with the squared gamma-2 functional of t. Now, however, we have already seen in the first talk that this is equivalent to the squared Gaussian width. This is the majorizing measures theorem. But still, people take this additional step to formulate this in terms of the Gaussian width. And the reason is that this parameter actually has a geometric meaning. So this is something we haven't seen before, so I thought I'd show you a little picture. So the picture is actually not for g of t, but g of t minus t. So this expected soup here. So what you can do is divide the standard Gaussian by its norm and pull out the expected norm here. And that will give you some constant which is universal. Universal depends only on n. Doesn't really matter what it is. And then this g over its norm is uniformly distributed on the unit sphere. Okay, and now this quantity, what does it actually say? It says for a particular realization of this here, look in a random direction on the unit sphere, and then measure the width of that set in that direction. Okay, and then afterwards, when you compute the expectation of this, you're actually averaging over all these possible directions. Okay, giving them equal weight, so to say. So this is the geometric meaning of this parameter. Okay, so let me give you a proof sketch, which is based on this paper of Liao et al. So what they actually showed is, okay, and if you don't know what a sub-Gaussian matrix is, simply think about a random sign matrix. If you have such a matrix with isotropic, one sub-Gaussian independent rows, then the following process, so phi x normalized minus x in the L2 norm, has actually sub-Gaussian increments. This is something you can show. And actually, Shechtman also already proved this in 2006 in a paper for Gaussian matrices, but he heavily used all sorts of properties of Gaussians, like rotational invariance that you don't have for sub-Gaussians. So to me, it was sort of a little surprise that this also works for this more general setting. Okay, and once you have this, you can actually deduce the result with generic chaining in the most simple case that we saw this morning. So really the vanilla generic chaining argument. So, and I want to add a little twist to it is that Jelani already mentioned. So what we've seen this morning is that if I have a process that has sub-Gaussian increments with respect to some metric, so in this case simply the Euclidean metric, then I know that the expected soup of this is controlled by the gamma-2 functional. Okay? Okay, so that's the result for P is 1. What you can actually do is make a very, very simple modification of this generic chaining argument and also get LP bounds. And the LP bound will look as follows. You have the gamma 2 functional plus the square root of P times the diameter of T. Okay, and as we've seen before, this means that the upper tail of the distribution of this soup will be sub-Gaussian again. So it will decay at least as fast as Gaussian. Okay, so let me show this. So if you have this bound for all P, then you can do Markov's inequality with P and then optimize over P, and then you get the following tail bound. Okay, and this tail bound is in a certain sense sharp. So let's look at the following scenario for simplicity. So let's look at the canonical Gaussian process that we've talked about a lot today. So I simply take inner products with a standard Gaussian vector. Then this process is sub-Gaussian with respect to the Euclidean metric. So I know from, first of all, the generic chaining argument and the majorizing measures theorem that we both saw this morning, that this expected soup is equivalent to the gamma 2 functional. In addition, I know by Gaussian concentration of Lipschitz functions that this soup of the canonical Gaussian process concentrates around its expected value like a sub-Gaussian random variable. Okay? And if I put these two observations together, I get this bound. Okay? So for Gaussian processes, this bound that we have here is actually weaker than what we already know. Okay? Because actually in this probability estimate, we also have an estimate for the lower tail of the distribution. Okay? Where this is only the upper tail. However, the nice thing about this bound here is that it not only works for Gaussian processes, but also for sub-Gaussian. Okay? And okay, I'm willing to make a little meta statement here, so you can use a little trick that I'm about to show in essentially any chaining argument that I've looked at and can get sharp tail bounds. Okay? So this is the simplest possible case, but it also works in more difficult chaining arguments. So very simple trick, but effective. Okay, so now let's have a short look at how to prove this, this bound, and it's a simple trick. Actually, we already saw it almost in one of the talks. So what I'm going to do is I'm going to fix an admissible sequence, and then I'm going to look at level log of P. And now I'm going to look at the LP norm of the soup of xt minus some anchor point. And I'm going to split it into two parts. So I'm going to take pi L of t, so this is the approximant to t in set TL. Okay, so the Lth approximation set. And I'm going to split this in two parts. So I look at xt minus x pi lt and this remainder. And now the thing we already saw this morning is that I can actually estimate this second part very easily. Because this set has only 2 to the 2 to the L elements, I can simply estimate very crudely the soup by a sum, and then estimate this sum by the largest term, okay, which I will get TL times, and this will then appear with power 1 over P. So this guy is bounded by 2. And in addition, because I know that the process is sub-Gaussian, I can estimate these terms by square root P times the soup over T and TL of the distance between T and this anchor point. Okay, so that's the easy part. And now the additional observation that you have to make is that you can run the generic chaining argument as Jelani explained it this morning and actually show that this remaining part can be estimated by something that doesn't depend on P, simply by the gamma 2 functional again. Okay, and that's it. Okay, so now let me finalize the proof sketch to get back to Gordon's theorem. So I've now adapted it, so assume that phi is a standard Gaussian matrix or a random sign matrix. And we want to show that under this condition, this rescaled version is an epsilon isometry on T. So it approximately preserves distances in the set up to a little epsilon. Okay, so you simply combine these two theorems. So now we know that we can write this guy as the sup over Zx minus Z naught. And we just learned that this process Cx is sub-Gaussian. And now I can plug in this tail bound for this guy and estimate this with high probability by this gamma 2 functional plus u over square root m times the diameter of t. T is in the unit sphere, so this is a constant. And I get this estimate, okay? And this is smaller than epsilon if this condition holds. Okay, maybe as a little small thing, earlier I defined the restricted isometry constants with squares here on the norms. It doesn't matter, okay? You can derive that result from this one here. Yep. No. He simply used properties of Gaussian processes. So he didn't use any chaining at all, actually. Yeah, but all results for sub-Gaussian is the. Yeah. Yeah, that's right. Okay, so yeah, so this is very nice, right? So we now have a good dimensionality reducing map that is, in many cases, doing an optimal job. However, there's a big downside to this map, so I don't know. I have computer scientists here. Who knows what it is? Okay, so actually, it's very slow, right? So this is very slow. So it's a densely populated matrix, completely filled. So it's slow. And actually, for some applications, it's too slow. So let me show one. So let's look at the problem of computing least squares estimate under some constraint. Okay, so I take some coefficient matrix. C is a closed convex set. And let's say that X opt is the least squares solution under this constraint. So the least squares solution, which is in this convex set C. So there are many interesting instances of this program. So if I take RD, this is simply unconstrained. If I take a rescaled L1 ball, then I get the lasso that promotes sparse solutions. And if I take a rescaled L1 and L2 ball, I get the group lasso, which promotes block sparse solutions, for example. Okay, and now we might be confronted with a high-dimensional problem, which will be expensive to solve. And the question is, can we use dimensionality reduction, or sketching, as it is also called, to speed up the solution of this program, or to get an approximate solution? So what do? We embed all the data we have in the high-dimensional space into a lower-dimensional space, and simply try to compute the estimate there. So this means, in this case, I embed the coefficient matrix A and this target vector B. Okay, I compute the solution, and now the ham question is this also a good solution for the original? Okay, so this was first analyzed by Sarlos in 2006, as far as I know, for unconstrained least squares. And the thing to note here is that if both phi and A are dense, then actually the embedding time will be more than the time to solve this program. Okay, so this is rather silly. Okay, so this means that, in particular, that if we use a Gaussian matrix or even random sign matrix, then we won't get anything. So the main question is, yeah, what did Sarlos actually do? And he used some new material that came out at the time that allowed to construct random matrices, good embedding matrices, that actually support fast matrix vector multiplication. So this is what I'm going to talk about now, about fast and sparse Johnson-Lindenstrauss transforms. So these are transforms aimed at basically the following. So the goal is essentially to get as close as possible to the results that we have for Gaussian dimensionality reduction, but at the same time making a construction that has smaller embedding time. So there are basically two lines of thoughts here. So there are fast Johnson-Lindenstrauss transforms and sparse Johnson-Lindenstrauss transforms. So let me mention the first one briefly. So this idea came from a paper of Aylon and Chazelle. and was later more developed. And I can be rather brief about this. So let me summarize the construction as follows. You take the matrix from the previous talk. So you start with a discrete Fourier transform, subsample the rows, and the only additional thing that you do is that you randomize the column signs. And that's actually the purpose of this diagonal matrix with independent random signs on it. Okay? And there's a bit of rescaling going on here, and this rescaling is done so that this map is at least in expectation an isometry on each vector. Okay, and you can do several things here. You can take a discrete Fourier transform, Hadamard transform, also circulant matrix. The idea is always the same, that you can use the FFT to do matrix vector multiplication. So in particular, computation time is n log n. Okay, and now I have a nice spoiler. So actually a result of Oymak, Bemi Recht, and Madi, who's here. They showed that you can get some sort of version of Gordon's theorem for this embedding. So Madi will explain this tomorrow. So, okay, so that's a bit of a teaser. What I want to look at is a different line of work, which is concerned with sparse Johnson-Lindenstrauss transforms. And the idea is quite simple, and I think you can correct me if this is not right, but the first source where I saw this is the main idea is that you start with a random sign matrix, but you try to sparsify it. Okay, and what Aglioptas actually did is he said, I'm not going to fill my matrix with random signs, but actually with, let's say probability 1/3, I'm going to put a random sign in the entry, probability 2/3, I'm simply going to put a 0 there. Okay, and what he showed is that you can still get a good embedding, so he proved a version of this Johnson-Lindenstrauss lemma for this particular setting. Okay, and that showed that you can at least get a constant sparsity factor in your matrix if you do that analysis. And then later, people looked at this again, and the interesting thing that they showed is that you can actually get a sparsification of the matrix that goes beyond this constant level. Okay, so I think the analysis started in this paper, and later other people worked on this. So I'm going to take a very intuitive implementation from a paper of Daniel Kane and Gilani. Okay, and it runs as follows. So start with a random sign matrix, and then for each column independently, select S elements uniformly at random. Okay? And these elements you keep, the rest you zero out. Okay, so this leads to some selector variables delta ij, which are 0, 1. And then you get a sparse Johnson-Lindenstrauss transform by rescaling it by this sparsity factor S. Okay, so first remark is that this is again an isometry in expectation. And because I have S non-zeros per column, I can compute this in time S times the sparsity of the vector that I'm embedding. Okay, so this is this zero norm here. Okay, so in general, this fast Johnson-Lindenstrauss transform and the sparse one have incomparable running time. Okay, and the question that I'm now interested in is the following. So can I create a sparse analog of Gordon's theorem? So can I state a result that tells me if you give me a certain set T, in which embedding, in which dimension I can embed this set? Okay, so let's formulate a bit easier version. So I'm not going to ask for a high probability version, but I simply want that this best accuracy that I can get, so this restricted isometry constant epsilon t, is smaller than epsilon in expectation. Okay, so this is the formalization of this question of a sparse analog of Gordon's theorem. Okay, and the answer that I will show in a minute will again depend on an appropriate complexity parameter of this set T. So in the case of of Gaussian dimensionality reduction, where I use a Gaussian matrix, this complexity parameter is the squared Gaussian width. However, in this setting, that cannot be the right complexity parameter for the following reason. So if I take my set T and I apply an orthogonal transformation to it, so I rotate it, then if I have a Gaussian matrix phi here, then this doesn't do anything to this question, okay? Because the Gaussian distribution is rotation invariant and can simply absorb this rotation, okay? So the answer doesn't change. So therefore, it's also natural that you get a complexity parameter that is rotational invariant. So this squared Gaussian width. However, in this case, if we work with this sparsified transform, then this rotation will mess up the structure of the matrix. So it has to be more complicated, and it will be. Okay, and also there's some sort of interplay going on between the embedding dimension that you can achieve, the column sparsity that you can enforce on the matrix, and also the structure of the set T. So let me summarize some previously known results. Jelani worked a lot on this. So if I take a finite set, so this is the setting of the Johnson-Lindenstrauss lemma, then what you can show is that you can embed into the same dimension, so epsilon to the minus t times log of the number of points, so this Gaussian embedding dimension. But you can actually sparsify the matrix quite a bit. So you can set S to be epsilon times M. Okay, and epsilon is this accuracy parameter that models how well we approximate distances between, or preserve distances between points in the set. So this epsilon is actually a small number. Okay, so you can save quite a bit, and you can save really a sub-constant amount of computation time. Okay, then things become even better if I have a data set that lies on a low-dimensional subspace. So if I look at T to be the intersection of some d-dimensional subspace with the unit sphere, then I can embed in essentially the same dimension as in the Gaussian case. So epsilon to the minus 2 times d, so the squared Gaussian width of a subspace is actually d, times some polylog factor. However, I can significantly sparsify this matrix, so I can let S scale basically as epsilon to the minus 1. So this dimension doesn't appear there at all. Okay, so that's pretty good. However, there's also sort of a negative result. Namely, if I take for T the set of all k-sparse vectors in the unit sphere, and I set this accuracy parameter to be constant, then if I want to embed into the same dimension as in the Gaussian case, which is optimal in this case, then I cannot sparsify the matrix. Okay? So there's some interplay going on, and what we would like to discover is whether we can create some sort of new complexity parameter for this set T that will describe how I can set M and S to get a good embedding. Okay, so here's the new complexity parameter, and this will look a little bit funky. So let me first of all explain what all these elements are. So these GJs are IID standard Gaussians. These eta J's are IID Bernoulli variables with mean QS over M log S. Okay, and this Q is a parameter ranging between 1 and M over S log S. Then we do the following. In the first brackets here, you see something like the Gaussian width, except that we've stuck in here these Bernoulli parameters, these 0, 1 variables. Okay, so it looks a bit similar like a Gaussian width, but with some cancellation here, or some zeroing out, to be precise. And then afterwards, we take the LQ norm with respect to these Bernoulli random variables, and then we rescale. Okay, so to give a bit more feeling on what this parameter is, let me show that it's in a certain way sandwiched between the Gaussian width. Okay, so this parameter that we had before. So if you take Q to be equal to M over S log S here, in which case all these Bernoulli random variables are identically equal to 1, then I simply get here the Gaussian width back with some new scaling. Okay, so a lower bound for this complexity parameter is gt over square root m log s. Okay, on the other hand, I can apply a result from probability in Banach spaces, Kahan's contraction principle, to get rid of these Bernoulli random variables, and in that way show that this parameter is also bounded by 1 over square root s times the Gaussian width. Okay? So the important thing to note here is that in this lower bound I have scaling 1 over square root m, and here 1 over square root s. Okay, so I will now show the main result that we have in this direction, and show the meaning of these two bounds. Okay, so here's the main result from our paper. So suppose I do the following. M should scale like the squared Gaussian width over epsilon squared up to some polylog factor. And S should scale like 1 over epsilon squared times some polylog factor. And then I can show that the expected restricted isometry constant is less than epsilon, as long as I pick S and M such that this new complexity parameter is smaller than epsilon, up to some polylog factor again. Okay, so there are two remarks. So first of all, this first condition is redundant up to log factors. So why is that the case? So if I require that kappa t is less than epsilon, then because of this first bound, I see that M should scale at least like the squared Gaussian width over epsilon squared. Yep? That would be the case if they were random signs. But they're actually 0, 1 variables, right? So they have the effect of zeroing out some of these Gaussians. Okay, so because of this first condition, this one is redundant. And actually what we believe is that a lot of these log factors that appear in this result can be removed, but this is not necessarily easy. Okay, so maybe I will talk a little bit about this later. But for now, I'm simply going to introduce some new notation to clean this all up. So I'm going to introduce this inequality with a star under it if I want to hide any number of log factors. Okay, and then I can rephrase our result as follows. The expected restricted isometry constant of this sparse JL transform is an expectation less than epsilon, as long as these two conditions hold. Okay, and now this result is still implicit, right? Because both S and M are intertwined in this complexity parameter kappa t. Okay, so if you want to look at a specific scenarios or a certain set t, then you still have to estimate this, but you can use this. You can use standard tools for this. Okay, and we work out many examples in the paper actually. And what we find is that we can recover all the known results that were known for specific sets. So in particular, the ones that I showed before, but in a qualitative way. Okay, so we have all these log factors in the way, which make it suboptimal. Okay, but at least qualitatively, we recover the right parameters. And we also get some new results for unions of subspaces and manifolds. Okay, so I want to show some of these applications. But first I will say a little bit about the proof, and this is really a little bit. So the proof is as follows. We have a simpler proof for the case that T is a subspace intersected with the unit sphere. And then for general T, the strategy is to reduce in many, many steps to this subspace case. Okay, so this is the only thing that I will say at this moment. And let me also say something about the proof ingredients. So at the basis of this is a generic chaining argument for suprema of second order chaos processes, or to link it up with your talk, with degree 2 polynomials in Rademacher vectors. Okay? And then we use a lot of tools to control covering numbers, like Moray's lemma that we already sort of saw in the last talk, dual Sudakov inequality we've also encountered before, and entropy duality. Okay, so if time permits, I will show some of this, but probably not. Okay, so let's look at what kind of results you can pull out of this. So let's look at the case that that E is a d-dimensional subspace and T is the intersection of this subspace with the unit sphere. And a parameter that will play an important role is the incoherence of this subspace, which is the incoherence of the basis of this subspace with the unit basis. Okay? Or formally, you look at the maximal norm that you can get when you project a standard basis vector onto the subspace. Okay, and this parameter is between 1 and square root d over n. And then the expected restricted isometry constant of this partial transform on this subspace is smaller than epsilon when the embedding dimension scales like d times epsilon to minus 2. And the sparsity scales like this, like epsilon to the minus 2 times the squared incoherence parameter. Okay, and if this incoherence is very small, then you can really set S very low, so as low as 1, okay, in very good cases. Okay, now I want to get back to this least squares application. So I want to show one result where you want to make a sketch for the lasso. So we want to find the least squares estimate under an L1 restriction. Okay, so a program that promotes a sparse solution. Okay, we call xopt the minimizer for the original program, and xs will be the optimizer for the sketch program. And now the following parameter plays a role. This is the smallest singular value of the matrix A, this coefficient matrix, when you restrict it to a scaled L1 ball. Okay, and now you can say the following. If you know that the optimal solution is k-sparse, and you've taken the right radius here, then you can if you set m, this embedding dimension, to scale like the maximal column norm of this matrix A times this inverse squared smallest singular, restricted smallest singular value, and S to scale like the largest squared element of the matrix, then with high probability, the solution of the sketch program will be very close to the solution of the original program. Okay, with this being the error factor. Okay, and people showed before that in the Gaussian case you can get this embedding dimension, and what we get out of this result that you can really significantly sparsify this matrix and really get a speed up of this program, which is not possible with Gaussian matrices. Okay, then I think I'm going to skip this. The last application I want to show is to manifolds. So suppose I have a d-dimensional manifold that is created in the following way. It's the image of the Euclidean unit ball by a map that is both by Lipschitz, and also I want its derivative to be Lipschitz. Okay, so it's a Lipschitz manifold. And then I'm going to use the following notation. So for any x, I let Ex be the tangent plane to the manifold at that point. And then Tm is the tangent bundle, so simply the collection of all these tangent planes. And then I'm going to define a parameter, which is the largest incoherence that appears among all these tangent planes. Okay, and then what you can show is that if you choose the embedding dimension to be epsilon to the minus 2 times, well, let's say the intrinsic dimension of this manifold, right? So this is a d-dimensional object. and S to scale like, so the column sparsity of this sparse Johnson-Lindenstrauss transform to scale like alpha d squared. Then what you can show is that you preserve geodesic distances, so intrinsic distances on a manifold up to an epsilon. Okay, and this result is in a sense optimal in the sense that if alpha is relatively large, so this incoherence parameter, then you can construct a bad manifold that shows that you cannot sparsify the matrix in general. Okay, are there any questions so far? Okay, if not, then I want to say something about the proof. And what I want to focus on, because this workshop is about chaining, is about the chaining result that is the basis of this. Okay? So what we're going to do as a first step is write this restricted isometry constant as a second order chaos process or a degree 2 polynomial in a Rademacher vector, so a vector of independent random signs. Okay, so this is the expected restricted isometry constant. And what I noted before is that in expectation it's an isometry. So if I take the expectation with respect to sigma here, so remember that sigma are the random signs that are used in the original matrix. And these delta ij model which of these I keep in the matrix if they're 1. And if they're 0, I zero these random signs out. Okay, and I know that this map will be an isometry in expectation. So since all my vectors lie on the unit sphere, this expectation is always 1. Okay, and now I'm going to write it as a degree 2 polynomial in a bit of an artificial way. So we can write phi x as a delta x times vector sigma, where sigma is simply a very long vector where I've stacked all the rows of this original random sign matrix into a vector. Okay, and then I can write the following, where this matrix A delta x depends on delta and x, and it's simply the matrix which is block diagonal, and on each block I have a vector, which is the original vector x, where I've taken a pointwise product with the selectors of the ith row. Of the ith column. Okay, and these are put on the diagonal. So this is a simple computation to verify this. And then you can write this restricted isometry constant as the soup of a so-called second order chaos process. Okay, and then you think, well, what for, right? I mean, this looks totally artificial. We do this to use a chaining result out of the box. So the chaining result looks as follows. Now we want to estimate this degree 2 polynomial. And the general result reads as follows. So as far as I'm concerned, the important work was done by Kramer, Mendelssohn, and Rauhut. They proved the bound for the expected value, and the only thing I did was improve the till bound. So let's look at the following. So we have a set of n by n matrices, which is called curly A. And then we take independent random signs, sigma 1 to sigma n. I let this be the operator norm of a matrix, this the Frobenius norm, and dfa is the largest Frobenius norm that I can find in my collection of matrices. And then what they showed is that I can estimate this expected soup by the gamma 2 functional squared of this set of matrices with respect to the operator norm, plus the radius in the Frobenius norm of this set times this gamma 2 functional again. Okay, and the corresponding till bound looks as follows. So this is an upper till bound, so this term is the same as this, so it's simply the upper bound for the expected value. And then the tail behavior is governed by the largest Frobenius norm of A star A, where you select any A from curly A, and by the largest operator norm of A star A that can occur in the set. So I think this is a little bit disguised, but we've actually, for curly A to be a singleton, so where I actually don't take a soup, but I only have one matrix, this is actually the Hansen right bound, okay, that we saw in the second talk today. Okay, so now let's first see how to use this. So I started with a restricted isometry constant of this sparse GL transform. I rewrote it as the soup over degree 2 polynomial in a large vector of random signs. And now we can apply this theorem for the following set of matrices. These matrices A delta X, which are these block diagonal matrices. Okay, and then the parameters we have to compute, remember, is first of all the gamma 2 functional in the operator norm of this set of matrices and the radius in the Frobenius norm. So if you calculate the operator norm of a difference of these two matrices, then you get the following norm that you can simply express in terms of these deltas and the vectors x and y that you actually start out with from the set T. So it looks a bit like the Euclidean norm, but where you zero out some coordinates, okay? And these coordinates are zeroed out according to the selectors for the ith row, and you take the max over all rows. Okay, so this gamma 2 functional of curly A with respect to the operator norm is equal to this thing here. Okay, and since what you can also easily compute is that the Frobenius norm of one of these matrices is simply the L2 norm of the original vector that you started out with. These all lie on the unit sphere, so this Frobenius diameter is simply 1. So this theorem of Kramer, Mendelssohn, and Rauhut implies that you can estimate the expected soup with respect to these Rademachers in terms of these two guys. Okay, and now the only thing I have to do to get the expected restricted isometry constant is take the expectation with respect to these selector variables, delta. Okay, so what in the end the proof of this theorem that I showed boils down to is actually computing this guy here. So this expected squared gamma 2 functional, then you also have an estimate for this guy. Okay, so this single parameter sort of controls how large this restricted isometry constant is going to be. And estimating this parameter is really the main technical work of the paper. Okay, however, I'm not going to show this because this is a workshop on chaining. So what I'm actually going to do is show how you prove this, this bound here, this generic chaining bound. So I want to show a proof sketch to finish my talk, I guess. So let's look at the result again. I start with a set of matrices, m by m matrices. I take independent random signs. I form this guy here. A is the this is the operator norm. This is the Frobenius norm, and this is the diameter in the Frobenius norm. And I want to show this estimate for the expected value. Okay, and the basis of this is a cute little chaining argument that is sort of catered to this special case. So it makes use of the structure of the problem. Okay, so there are basically two ideas. So the first one is to use decoupling. So we already heard about this in the second talk. And in this case, you can use a very simple form of decoupling. So if you write out what this is, so you write out the square of this norm minus the expected value, then you actually get a degree 2 polynomial in these independent random signs where you've zero out the diagonal elements. Okay, so this expected value, these will be exactly the diagonal elements of this degree 2 polynomial. Okay, and if you have an object like this, then you can always decouple it. So there's a small constant 4 hidden here. And this means that you can replace the sigma j's by independent copies. Okay? So these will be independent random signs, which are in turn also independent of the original random signs. Okay, and this you can rewrite as a degree, no, not a degree 2 polynomial, but like sigma transpose times A transpose times A, and then the independent copy of sigma. Okay, and we want to compute the expected soup of this. Okay, and this is the point where the chaining comes in, and we're actually going to do a special chaining argument that makes use of this product structure of the coefficient matrix here, of A star A. Okay, so what we're going to do is a bilinear chaining argument, where you sort of chain on both sides simultaneously. So you take an admissible sequence for this set of matrices, and these pi n's of A, these are actually the, you can sort of view them as the approximants of A at the end level. Okay, so pi n of A is in Tn, the end element of the admissible sequence that you choose. Okay, and then we do the chaining argument, and the first thing you do is write down this chaining identity, which is this telescoping sum. Okay, so you write this out as an infinite sum of these differences here. Okay, and now you add and subtract the following term, sigma pi n minus A star pi n A sigma prime, and then you get two terms here. Okay, and now the main observation is the following. What I'm now going to do is look at this first term, S1A. And remember, I want to estimate all these terms in a good way. And what I'm going to do is I'm first going to forget about this dependence in sigma prime. So I'm simply going to take this fixed. Okay, and I'm only going to work with this original vector of random signs. Okay, and now Hafting's inequality says that with high probability, so probability 1 minus e to the minus u squared, I can estimate this guy by this term here. So by the L2 norm of everything that you see here except this sigma here. Okay, times u. Okay, and then we split these two parts. So I estimate out the operator norm of the transpose of pi n minus 1. So this is this operator norm here. And I'm left with this part here. And now I'm going to simply estimate the second part here trivially. So I'm simply going to take the soup over all possible matrices that I had in my original set here. Okay? Okay, and if you use this as an ingredient in the chaining argument as Jelani outlined it, so with these successive bounds, then you end up with the following bound. So you can estimate this first, the soup over this first sum, so the soup over this sum here, by the gamma 2 functional times this soup over A applied to sigma prime. Okay, and we're only using the probability in the original random signs here, okay? So we haven't done anything with these independent copies. And now what we're going to do is take the expectation with respect to sigma prime on both sides. Then we get this here. And then we're going to simply estimate the expected soup of A applied to sigma prime here by the L2 norm. Okay, so this is simply Jensen's inequality. And now since sigma prime and sigma are identically distributed, it's the same as replacing the sigma prime by sigma here. Okay, and you get a similar inequality for this second term. And what you then find is if you subtract and add the expected norm of A sigma squared here, so A applied to these random signs, is a quadratic inequality for this quantity here. Okay, so remember, this is what we started out with. and we get an estimate in terms of its root. Okay, and then if you solve this quadratic inequality, you're done. Okay, and that's the end of the proof, and also the end of my talk. Thank you. Are there any questions?